So good afternoon, everyone. So first of all, I would like to thank Fabian and the organizers for inviting for this presentation. I'm going to speak about Markarian multiwavelength data center. So this is a platform that was developed in my group. So the idea is to provide data and tool for modeling the emission from blazar. If I highlight here, there are three words: blazar, accessing data, and modeling data. So this is the structure of my presentation. I would like to start to some small introduction about blazar, then why these data are important, how we can access and how we can use for modeling. So if you take any classical textbook, so the definition of the blazar is that is an AGN which has this jet that is starting from the supermassive black hole to the direction of the observer. And because of this, you see many different features of this object, but these blazars are powerful but very rare objects. Why rare? Because if you take the number of the known blazars, I mean the sources that we can classify blazars is between 6,000 and 7,000. So if you then compare to the total number of the galaxies that we know, so this is a very small fraction. So there's the question why these objects are so interesting that people, even Marina this morning mentioned about the multi-wavelength data from blazar observations. So I list some of the points that I believe that makes these sources interesting. So first of all, these are very powerful, the most powerful non-explosive sources in the universe. So the bolometric luminosity can be 10 to 49 erg per second. What is interesting for us is that the broadband emission is from radio to very high energy gamma ray band. And so yesterday was been mentioned that these are probably the sources of very high energy neutrinos, which make them even more interesting to study. If we make some kind of historical view, so the first quasars were discovered in 1963. So between 70s and 90s, this was the time when they were collecting a few data about blazars, understanding if they are galactic or extragalactic, etc. But in 2025, we are so advanced that we have so much data that we can study these objects not only using the photons, but neutrinos, multi-messenger data. So if you, for the comparison, so this is the same source, the data you could gather in 1999, and this is what you have in 2025. So this is a huge data that we are accumulating, and so the research in blazar has turned from single epoch, single observation to multi-wavelength, multi-messenger, and multi-temporal study. So we have a lot of data that we can study. And as yesterday Fabian also mentioned, the problem is this data is scattered everywhere. So you have different data centers, the catalogs, everywhere that you can find this data. But if you want to have the source where you can just collect everything and try to understand your object, this is quite difficult. This is why we started this Markarian multi-wavelength data center. Why Markarian? Because there are two famous blazars, Markarian 401 and Markarian 421, and they were discovered by Benjamin Markarian in Armenia. So this is why we thought that this is about blazars. We can name about these discoveries. So there are two main functionalities. So this is the back end of the data center. So there are two main functionalities. So the first one is the data, and second one is the theoretical modeling. So we provide both possibilities for the users. So you can get the data, you can model them. So I would like to explain both of them. So the first, the data. So of course it is important which kind of data we are providing. So if you just provide the cataloged data, this is fine, it's good, but it's not really the full that the researchers need and they can do science. So this is why on top of the cataloged archival data, we are providing also the new observations. Here are some of the bands that we have the new data. So what is happening when you are making a search about a specific blazar, there is this, it makes the first search in all the catalogs that are available for blazar observation and retrieves the archival data. Then what is happening, you are on top of this, you have a real-time data that you get from SSS and ZTF or UVO data that is already pre-analyzed and stored in our data center. All of blazars that has been observed by switched UVO. In X-ray band, all the blazars that has been observed by XRT new star, and also the gamma ray data. So just to demonstrate what is the difference between the data that we are providing and what you can get from the catalogs, let's say. So this is a source that if you make a query, you can collect this amount of data for a blazar. So this is what we are providing. So you see that in the many places we have a significantly large amount of data that we are providing, and this data is pre-analyzed and science ready, so you can just download and make your research. Here are some of the things that I already mentioned. So this is archival data that is done by using this view blazer tool that was developed by Paul Giomi and his colleagues. So this is where you collect all the archival data. Then real-time data are collected from ASAS, SN, and ZTF when you make this query search. The UVO data are pre-analyzed and stored for all of the blazers. The same for X-ray and NuStar and Swift XRT. But I would like to highlight the gamma ray data, because in gamma ray band we have the Fermi satellite that is continuously monitoring the sky. So this means that you have a very significant information in the gamma rays that you want to use. But what is happening if you just access the catalog data that is available in different years, you are just summarizing everything. So this means that the information that is present in your data, you are kind of missing it. So this is the typical behavior of blazars. So this is the light curve. So this is in logarithmic scale. You see that there is like order of magnitude to 3 orders of magnitude change in time. So when you are taking the catalog data, basically you are just trying to average from here to here. It means that all the variabilities, spectral changes you are missing there. So this is an example of the zoom of this part. You see that not only the flux is changing, but also the photon index. So it means that in some cases you have the change of the emission spectrum or etc. So this is what we do instead of to just have this averaged one. We split this light curve with the Bayesian intervals, and for each of them we are performing the spectral analysis. So it means that in a specific periods you know how the emission of your spectrum of your source is changing. Just to demonstrate, these orange points that you see here are the catalog, the averaged, time averaged ACDs that you get from the Fermi catalogs. But this all different colors data is the one that you get from when you make these blocks in the light curve, and you see that there is a significantly different information than whatever is available in the catalog. So this is this provides a lot of possibilities to understand the time-resolved analysis of your sources, so you can understand what is happening of your object. So just to demonstrate how this works, so this is the interface of the data center. So there are these different so both is where you provide the information about the source. There are the list of the gamma ray blazars, or the list of the ones that are non-blazar. So you can just select the source from this list. It brings here, so you just, when you make the plot, so it is just going to the catalogs, archival data, brings back the additional data that I have presented. So this is all the data that is available. The same thing you can do, just typing the name of the source that you are interested. It automatically recognizes the coordinates and bring back to the spectrum. So this is an interactive, so you can play with it. So you want to see an optical or X-ray, so you don't like the X-ray data, you can just remove this X-ray data. Or if you don't want to you want to include the specific X-ray measurements, you can just really play with your data. There is also the possibility to filter to it. So you can just, like you do in your laptop, so you have the data, you can just apply different filters, and you can try to investigate what is happening with your source. There is also there is this set light curve animation. Why it is interesting? Because it shows also in time how the emission spectrum of your sources is changing with the simultaneous data. So you can have also the feeling to see in different periods which components were dominating and what was happening with your source. And this is actually quite good because you can do the time-resolved study of this object. So this is the part of the data that you can get the data, but for blazars or any type of astrophysical object, so it's interesting to, our goal is to understand this object. So the data is showing what is happening with them, but our final goal is to understand from the theoretical point of view which processes are taking place in these sources. No, so this is why the second component is the modeling, where we use these convolutional neural networks. So I would like to show what this means. So there are two main theories of laser emission. So it are divided based on the particles that they are starting the emission. So in the case of leptonic scenarios, these electrons are injected inside the jet, which are emitting by synchrotron radiation and by inverse Compton scattering. And in the second scenario, which is the hadronic, so when the protons are interacting, this is where you have also the neutrino observations. So this high energy component here is due to the either direct proton synchrotron emission or from the secondary. So this is just general view of the processes. Of course, there are much more details, more interesting things, but just to give you a feeling what's the processes. And Well, from the theoretical point of view, what means the modeling? So it means that you have your model, you have your own data. So statistically, you want to understand which are the parameters that best describe your data. So if you take the theories together with the data, they develop it quite well. So now if you want to have a model that fully takes into account the injection, cooling, interaction of all the particles, these codes are quite heavy to run. What means heavy, for example, if you have for a single parameter space, if you run the SEC or external Compton models, it takes like tenths of seconds, even 1 second. But for hadronic ones, this is around like between 1 and 2 minutes. For one parameter space, this is quite good, quite fast. But if you want to make the Bayesian inference, for example, you need to compute these parameters 100,000 times. It means that you need to wait from several days to tens of days to have, or you have to have large resources to make these things. This is a very well-known problem because this is why they apply different things of approximation. They are not looking at the time-dependent pooling or etc. This is where we come up with the idea that we can speed up everything using these convolutional neural networks. These are the few papers that we did last 1 year about how you can use these convolutional neural networks for your modeling of your source. Just I want to demonstrate what this means and how you develop it. So this is the hadronic scenario. So there are 10 parameters in your model. So each of them, by changing, you have the different spectrum. So for all of these parameters, we consider very wide range, from very physically unrealistic to the maximum possible ones. And from here, you select some representative sample of the parameters that they cover all of your 10-dimensional parameter space. There are statistical ways that you can do that. As soon as you select these parameters, what you do, you pass to your numerical code. In our case, it was the Soprano code that has been developed in my group. So this is the code that takes into account the cooling, everything. So we selected 7 million parameters and we put it to the computation. So we generated 7 million synthetic data, let's say. After you have this, you generated your synthetic data, you plug into your neural network. So what is happening, you have the input is the model parameters, and so the output is the spectrums. Basically, what is your network doing is learning the connection between the input, between the parameters, and the output of the spectrum. So as soon as you have this training, then you can forget about your numerical code, and you can perform your neural networks. I will show what is the advantage that now it's way faster than the numerical. So you get the same accuracy, but the time is much faster. So we use the convolutional neural network. So here are some details, what are the structure, etc. So this is not important. I would like to demonstrate what means the learning in this case. So on these two plots, this is the computation from the numerical code, and this is the layers, this is the loss function, and now you see when you put it starts to change the network such that tries to explain your observational, your spectrum that you generated from your numerical code. So after some epochs, finally you have the neural network that are fully reproducing your computation from your numerical code. So this means that it's trained. Okay, there are ways of testing. I don't want to provide these details. So, but as soon as you do this, you have already the neural network that is you can replace with your numerical code. So we trained 3 different CNNs. So the first one is synchrotron Compton, which is good for BLAC type of blazars, external Compton when you have FSRQs, and of course leptohadronic ones when you have the neutrino observation. Especially I would like to mention about this one because there are a few codes in the community available, but none of them is able to make a real fit because this is too heavy from the computational point of view. You need to make really different assumptions. You need to fix many different parameters. You need to make really constraints. Still, you need to have a really large resources to do that. In our case, since these networks were trained, we are able to make the full posterior analysis of the model within a few minutes. So something was really impossible with the codes, with these neural networks. This lasts like 3 or 4 minutes. So this is the spectrum of this well-known blazar, Texas 546, and this is the parameters and the dependencies between each other. This is where we assume the Gaussian likelihood for the neutrinos. So basically, you assume that we have some neutrino emission at this level, which was reported by ICRANet. So this is so fast that even you can try different methods as well. So you can make this Poisson likelihood. So effectively, what you do instead of assuming any spectrum, you know that the number of the neutrino observation is 1 year, 1. in 1 year, for example. And every time the model takes the corresponding neutrino spectrum, computes with the ice-cube effective area, and finds the parameter that best describes your data. So this is something very nice because you very quickly you can make this analysis. If you have some multi-messenger observation, when you have some data, you can just perform this. This is available in MMDC as well. So how it happens? So there is this theoretical modeling section. When you select the hardware, for example, you can upload your data that you are interested. So this is the same data that I upload. You need to provide the distance of your object. Of course, you mentioned, for example, 180 in 12 months, so in 1 year, 1 event. Yeah, you provide your email address, and this is all. So you just push feed, you get the message that everything is done in the background. You get an email that is being processed, second email when it is ready, so between 3 or 4 or 5 minutes. Then it redirects you to the web page where the feed is done. You see all the parameters, you have the corner plots, everything. So everything what is necessary for your study. You just can plug the data. In a few minutes, we have the results that you can look and to see what processes were taking place. So this is just very quick, the user map of MMDC. This is data collected in 1 year and 2 months. So it's good that we have a lot of users from different countries that were downloading data from the feed. Just I would like to mention about the next step. So what we are doing is another project called Astro-Genesis that we are about to finish. So this idea is that we will change all of what I have mentioned to you. You will be domain-specified large language model that allows you to perform all of these things with the natural way. So you can just say model this natural event, get this data, etc. So the idea is that Astro-Genesis will make the simpler and the complex possible. So something like this hadronic modeling, you can by voice just say this neutrino, this period, model this data. This is in a finalizing stage. I think in 1 month or so we will have the online version. So you can try and test as well. So this is the conclusion. So we are open for collaboration. So if you have some data that we want to share, of course, with the corresponding reference about blazars, we are happy to do that. And for the future also, of course, it's Astro-Genesis. If you are interested, we can collaborate to somehow include this in Astro-Genesis. And the last slide, I would like to leave with this platform, Firmamento, that we developed with Paolo Giomi. So the idea of this platform that you can classify blazars in the sky direction, which is good, that you can be very useful if you want to identify where you have blazars. Thank you.